last presentation of the day. This is by Vanessa Sochat and Daniel Milroy from LLNL. They are recurrent speakers at this event, and today they are going to present how Flux Framework supports agentic science.
Hi everyone, my name is Daniel Milroy and I'm here together with my colleague Vanessa Sochat from the Lawrence Livermore National Laboratory. And we're going to be talking to you today about Flux Framework and how it supports the frontier of agentic science. So to provide you a little bit of background and motivation, what is the Flux Framework? Well, it's a system or user level workload manager developed by the Lawrence Livermore National Laboratory that combines two really important features: hierarchical job management together with graph-based scheduling. And if this is a little bit foreign to you, kind of this division of scheduling, job management, and workload management, hopefully by the end of this introduction, you'll have a little bit better idea of what we're talking about. So Flux actually recently joined the High Performance Software Foundation, or HPSF. We have over 25 contributors at this point, including some of the principal engineers who designed Slurm, which also originated at the Lawrence Livermore National Laboratory. So Flux was originally designed to address exascale and now post-exascale challenges by bridging the gap between traditional HPC-centric batch processing capabilities with the needs of modern, more dynamic workflows. And I'm going to tell you a little bit about how we do that and some of the features behind it. So first, I want to highlight that Flux runs on big computers or big clusters of computers. It's the system-level exclusive scheduler on the NNSA exascale system, El Capitan, which is currently #1 on the top 500 list. Flux is also scheduling 5 other top 500 supercomputers exclusively. And when I say exclusively or I say system-level scheduler, what I mean, again, is that it's the only system scheduler that's running on that particular cluster. Now, it has another deployment mode, or user level mode, that actually can be run as a job inside another system scheduler. And I'll talk a little bit about what that means and how that works in a second. So I first want to highlight that Flux's hierarchical modular design is a key to enabling really important features like portability, flexibility, and at the same time specificity in workloads. How does it do this? Well, you can think of Flux as being run as a job inside of another resource manager or scheduler, which could in fact be Flux itself if it's the system scheduler. So imagine, for example, you have a system that consists of a couple nodes that's being managed and scheduled by Slurm or Kubernetes or, again, Flux itself, and you have a job that wants to run in a particular way across just a subset of these resources. You can actually spawn a job on a subset. So for example, one of the 2 sockets of a 2-socket node, which then will create its own overlay network and then can actually further subdivide the resources. So divide up the cores and then create 2 sub-instances, which then are going to create their own overlay networks. So this enables a lot of really important features, like tailoring your scheduling decisions and scheduling algorithms to each one of these levels in order to match what those job needs are. It also enables tailoring of how the resources are managed themselves in order to optimize the work and how it's managed at each one of the levels to support the job needs. So in turn, this actually supports high throughput. So you can imagine a scenario, and this is what's done commonly, where a kind of encapsulating job is submitted that occupies the resources, and then sub-jobs or sub-instances are created within that job in order to further sub-manage those resources. So instead of submitting many, many jobs at the top level to the system resource manager and scheduler, you can create that encapsulating instance and then submit many smaller jobs at a lower level, perhaps with schedulers that are tuned to high throughput. The second feature is that actually Flux is designed to enable converged computing based on some of those important capabilities like hierarchical resource management and scheduling. Well, what is converged computing? It's actually bringing together HPC and cloud to get the best of both worlds in a seamless environment that supports both cultural and technological integration. So more specifically or more practically, what we mean by this in terms of what we work on is bringing Flux together with a de facto native cloud computing orchestrator, which is Kubernetes, into combine kind of seamless platform that enables AI and ML together with simulation-based workloads. So from the Kubernetes standpoint, it supports modularity, portability, automation, declarative management, etc. And from the HPC side, traditionally at least, HPC stands for performance, of course. It supports low latency, it supports sophisticated scheduling techniques, and high application scale, at least. Now, Flux, of course, supports all of those things, and actually some of the things that are interesting from a cloud standpoint, such as portability. And converged computing really sits in this space of creating a seamless environment that unifies all of these features together. Now, one of the first examples of this, the project that we created, was the Flux operator. Now, the Flux operator has a reconciler that creates and maintains a user-defined state. It creates a leader and a lot of followers that wire up together in order to create a Flux mini cluster. And this creates a fully functional batch scheduler inside of Kubernetes pods. So basically, it creates a Flux instance that manages and schedules those pods as if they're nodes. And this, in turn, bypasses the etcd bottleneck, which is well known. So if, for example, you need to create tons of different subjobs, which in turn require a lot of different creation of objects, you can instead create a Flux mini cluster and then submit jobs to that mini cluster. Now, this Flux operator runs on HPC, so think user space Kubernetes, and also cloud native Kubernetes environments. So a couple interesting features of the Flux operator. So we've actually tested it and orchestrated over 40 GPU and or CPU applications on up to almost 30,000 CPUs and 256 GPUs, which are used by agents and or autonomous scaling studies that I'll talk about in a little bit. The next thing I want to mention is Kubeflow and Flux are bringing them together to support AI and ML simulations. So this supports kind of low latency communication for MPI simulation in cloud native environments paired together with surrogate models, which is a pattern that we're starting to see happen a lot in AI native workloads and more HPC, kind of bulk synchronous parallel, kind of combining those with AI and ML models. So this is created via the Kubeflow trainer, which is the industry standard for AI and ML training. And what it wants to integrate is kind of traditional or support is traditional scientific simulations, which are informed by or steered by AI and ML models, which almost exclusively require GPUs. Now, those traditional scientific simulations, think, for example, physics-based simulations, are often CPU-based, but not exclusively CPU-based. In fact, some of the larger ones are GPU-based MPI tasks. However, the current Kubeflow MPI support was limited in terms of both the MPI variance and its requirement and dependence on kind of a slow, cumbersome, and difficult to configure SSH bootstrap. So by integrating Flux capabilities into Kubeflow, we were actually able to increase the MPI support and kind of bypass some of those requirements for SSH bootstrap. Now, the second thing I want to mention is that the Flux operator in particular affords elasticity and dynamism. So the Flux operator is designed to manage complex dynamic workloads that are required by coupled AI and ML simulations together. So again, think of, for example, you've got your traditional HPC-based simulation that requires MPI, but also maybe there are ML training components. So think, for example, ML training component, which requires GPUs. You have a couple different types of simulations. Maybe they're running in an ensemble environment or an ensemble setup, and you have an overall workflow whose resource needs evolve over time. So you start with ML training, then you can kick off maybe an ensemble of simulations A, which requires CPUs of a particular type, which during those runs will actually feed data into a machine learning model, which can be retrained, and then based on that, a second simulation can take place. So the idea basically is to create a dynamic HPC cluster in the cloud that doesn't require or doesn't over-provision resources. So again, you can provision the type of resources you need when you need them in order to save cost and improve utilization. We also support systems research and innovation. We're able to prototype novel scheduling algorithms based on our directed graph-based techniques, our graph match policies. So in other words, matching a query graph against the resource graph that represents the resources and the relationships in one or more systems, and testing how those different algorithms can be used in order to optimize for locality of jobs, to optimize for perhaps energy utilization, to optimize for how the storage system is used, for example. Now, I want to talk a little bit about the post-exascale crisis of complexity. As I've kind of alluded to before, our science is starting to demand orchestration, automation, and infrastructure. So think combining, again, traditional HPC features together with services. So from a traditional HPC standpoint, the workload tends to be a monolithic batch simulation, something that you submit via batch script on command line. The related resource model is node-centric, it's static, and has a static node-centric allocation. The management itself tends to be imperative. So think, for example, you have a user-specified fixed configuration and shape or topology of the resources and how they're related to each other. The interconnects tend to be fixed and human administrator managed, and the software discovery tends to happen via environment modules and is entirely manual or is just manual exploration of what exists on the system. The future is looking to be something very different. We're looking towards a converged HPC center at this point, which couples together AI ML simulations together perhaps with ensembles of MPI-based simulations. We have dynamic elastic resource graphs in terms of the resource model, which models kind of the resources and the relationships and how they might change in time. The management is evolving into declarative. So in other words, the user describes what the status is, and then the system is in charge of making sure that that status is aligned with what the user needs. The interconnect is virtualized, it's scoped, it can change, it represents dynamic or siloed to dynamic environments. And then the software discovery is via agentic methods or is evolving into a fully autonomous framework. So much of this is actually enabled by the workload manager, and that's why we were putting so much work into bringing in some of these features and supporting these features in Flux. Now, converged computing is really a transition. So it's kind of a middle point between traditional HPC and its evolution into where we're seeing support for agentic science. So our thinking has kind of changed accordingly. Convergence is really combining features, again, from HPC and cloud into a seamless environment that is the best of all these worlds together. And we started doing this in 2021 via the Fluence custom scheduler plugin for Kubernetes. Then in 2022, we launched the Flux operator, talked a little bit about that. That deploys Flux within Kubernetes and manages pods like nodes. Then as an extension to this, we created and started deploying users-based Kubernetes, which deploys on traditional HPC using Flux. Then in 2024, we embarked on a cross-cloud usability study in order to figure out what applications could be run in cloud-native environments and kind of more HPC-like environments in the cloud, and then compare those to HPC native-like environments and how they ran. Now, there's kind of a fissure between our old thinking and our new thinking that happened somewhere around 2024, 2025. So prior to 2025, we thought a lot about how do we just combine these features together. Now we're really thinking about how do we turn the entire center into an event-driven environment that supports these dynamic workflows. Starting in 2025, we started looking into HPC workloads that could be orchestrated by and represented by state machines in the cloud. So think, for example, we created a management framework that could actually manage the multi-scale machine learned modeling infrastructure in cloud-native environments. Then we moved on to agentic orchestration of HPC workloads in the cloud. So this is by creating autonomous scaling studies using Gemini. We're also thinking beyond convergence, beyond HPC and cloud convergence as a vision for an entire HPC center. And we're thinking kind of the year 2026 as the work that we're doing in terms of agentic job negotiation for hierarchical server architecture and creating agents for agentic science and kind of understanding the relationships between these agents in a hierarchical setting. This is related to national initiatives that you may have heard of, like the Genesis mission and the American Science Cloud, that seek to enable autonomous discovery, scientific discovery, and bring together U.S. national computing infrastructure, AI infrastructure, in order to solve large-scale problems. At the Lawrence Livermore National Laboratory, we have initiatives like the Future Generation HPC Center, which is going to be launched around the 2029 to 2030 timeline. So thank you. Now I'm going to transition to Vanessa Sochat. She can talk about the rise of agentic workflows in science.
Let's talk about now the rise of agentic workflows in science. We are moving from what we might consider traditional HPC or job submission toward agentic. So what does that mean in practice? What you're looking at here is a Slurm batch script. This is the way we've always run jobs, bread and butter HPC. We describe exactly what we want from a resource standpoint, exactly the modules to load, the commands to run, and submit it to the workload manager. Now what we're moving toward is more prompt submission. So we say, hey, agent, I need you to run my application with these resources, with these constraints. I need it done by Friday. And then it's up to the agent to figure out the details around that. And so I want to briefly tell you the story of how we got into this work. So early back in 2024, we were thinking about multi-cluster use cases. So the idea that you might have two clusters with two different workload managers, let's say Slurm and let's say Flux, and you might want to actually move your work from one to the other. What would that require? It would require a translation from a Slurm batch script to a Flux batch script. And so I'll tell you that when we first started this work, the correctness of those scripts was about 40%. Now when we do the same kind of work, the correctness has gone up to usually above 90%. So the agents are greatly, or more specifically, the models, the LLMs, are greatly improving in their ability to do tasks like this. And as Dan mentioned earlier, in the end of 2025, we took our questions to another level. We said, these agents are so good, let's ask them to do the entire scaling study. So that means building an HPC application, deploying it to Kubernetes, optimizing it, and then running the entire orchestration. It seemed like a really big ask at the time, but it worked immensely well. And this was our first white paper that we wrote at the end of 2025. We designed this agentic AI system, this agentic AI team, and we're going to talk about this a little bit later. Now, a big lesson that we learned, that we continue to learn, that many folks that are listening right now are also aware of, is that there's really a balance between autonomy and control. Where on the one side, you are totally controlling everything. You're not even using an agent at all. You're manually running things. And then completely agentic, where you're no guardrails. Agent, just do whatever you like. And if you delete my entire operating system, let me know. The ideal, of course, is in the middle, a balanced approach where agents have enough exposure to the environment where they can discover, they can learn, they can debug, they can figure out what went wrong, but there's guardrails so that they don't lead to destructive actions. Now, let me give you an example of this. An example is with SnakeMake, and we've been doing work where we actually have an agent write the snake file and then incrementally run each step. Now, as you know, with SnakeMake or any workload manager, this requires access to input data. It requires access to a working directory to write files, to delete when you need to roll back. And so complete control, this is a little bit like Goldilocks and the three bears. This one's too little and this one's too much. So complete control would mean that SnakeMake is manually run. I am the one to write the snake file. I am the one that stages the input directory and working directory, and I have to do everything. That's not ideal because I don't want to do the work. The other extreme is that you give the agent total access, unlimited to everything, and of course that can be bad. The balanced approach, of course, is saying, okay, the agent needs to have a read-only data input directory. Maybe we will link that to what starts out to be an empty directory with write. And then if the agent actually accidentally delete something in that working directory, it doesn't actually delete the initial data because that was read only. And so this is an example of a balanced approach where you've kind of considered the pros and the cons, and you give the agent exactly what it needs, but not too much. So let's now talk about what this meant for our agentic study back in 2025. We started with our agentic team. So what does that mean? Well, we start with a plan. This is a YAML file that essentially has the prompt. It maybe has some level of control where we define the agents that we want to use. We want a deploy agent that's an expert at deploying an application. We want a scaling agent, an optimization agent, and then helper agents such as a debug agent and a result parser. Now we give the plan to a manager agent. The manager agent is going to orchestrate the work and decide which expert agent to give work to. when we're running the expert agent, so let's say we just deployed and now we're scaling, here's an example of where the guardrails come in. So if the scaling agent has the ability to ask for as many nodes as it wants, there's no reason that it might ask for 1,000. And actually, I have seen this happen. Now, the guardrail that you'd want to put in place, of course, is to have an autoscaler that will physically prevent that operation from being successful. And then, of course, you can continue to the optimization agent and the result parser. I mentioned the result parser because it is an example of collaboration between human and agents. The result parser is going to generate a regular expression, parse the result file, get, for example, a figure of merit, show it to you, the human, and say, hey, is this look okay? Is this what you wanted? And then you can kind of proceed, cache that, and use it in future runs. And we were immensely surprised how well this study did. So I'm just showing you two of our applications, AMG and LAMPS. They most definitely strong scaled. And what we learned from this is, wow, we can actually perform things that were very hard before using agents. Because flash back to the previous year, 2024, we ran a performance study across clouds, and we did that manually, and it was very hard. And so what did we learn from this initial work to kind of step back even more? The first is that transparency is immensely important. So when we initially started, we started using frameworks like AutoGen, like LangChain. And what was troubling about that is that you can kind of read the code a lot, but there becomes a moment where you feel like a lot of it becomes a black box. And it's always changing rapidly, and you don't fully understand what's going on. The reason that we designed our own agentic framework, we call it Fractale, it's just very simple based on state machines and then agentic loops, is that we wanted to be the ones that were making every explicit call to the LLM, getting back the result, being able to understand what that format looked like, parse it, and then make the next step. This was important for our learning. The next thing we learned is how important prompting is, and this continues to be true. Whether you capitalize something, for example, that's important. The position that you put something in the prompt is important. Defining clear roles, goal, and context, this is all important. Next, as I mentioned, agentic science is collaborative. There are parts where you may want a human to come in and take a look at something. You also want to bring in human expertise via the tools that you make available to agents. And then, of course, guardrails. You need to have these guardrails in so that your agent doesn't just go totally off the walls and scale to 1,000 nodes, for example, or delete your entire operating system, and you will have a very bad day. And then finally, self-healing systems. So this is an ability to detect when something is going a little bit off, and then have a strategy for rolling back, for trying again, for alerting someone, but not allowing something to go off into basically terrible context drift. Okay, so how do agents fit into this future vision for an entire center? Let's talk about that. Let's think about this HPC center of the future. What might it look like? I'm going to give you just one idea. So in this HPC center of the future, we have some hub that has a number of child workers. We'll call it a fleet. Now, each child worker, it may be another center, it may be a cluster, it may be a single machine or an edge device. These are the units of workers that are able to, receive work, like I want to run this job. And so each worker has an automated discovery of resource providers, where a resource provider can be the workload manager, it can be storage or the file system, it can be the network, it can be your software. The idea is that you'd want to be able to bring up some kind of software that says, I have Flux Framework, I have SPAC. These are the number of GPUs that I have. This is what I can support to do work on this particular worker. We also want to be able to negotiate jobs. So imagine a job request comes into the hub. Hey, can you run this work? The hub should be able to say, let me check with my children workers, and figure out if we have a child that can run this work for you. And then, of course, let's say 5 children come in and say, I can do it, I can do it, I can do it, I can do it, I can do it. We would want to be able to then select the best across those contenders. And then, of course, we'd want to be able to dispatch. So you're going to be having coming in what might be just a prompt, a textual thing. Hey, go run lamps. And then we want to be able to convert that into the right format for the workload manager to use, a Flux batch script, for example. So it may not seem obvious, but I'm going to tell you that in order for a vision like this to work, we need to have agents that are going to run at multiple levels. And so let's talk about these levels. The simplest level is like deploying a server for agents to use on your local machine. You don't really need to think much about authorization or security. You're just kind of going to run it. The next level might be the cluster. So maybe you have agents that are interacting with your workload manager. And then the third might be at your center. So it's looking above all of your clusters, or maybe even above the center that's doing some kind of dispatch to multiple centers. So if you have some spidey senses, you may be saying, Vanessa, it kind of seems like as we move up this hierarchy, there's an increase in complexity of what you're managing and what you're trying to do, and security, because when you have something that's higher up that is exposed to more of the internet, more of the world, you need to have more security policy and precautions in place, and that is very logical. Okay, and so there's very different use cases paired with each of these things. So at the application level, this is where you're going to have, for example, agents that are experts for specific applications. At the cluster level, you might have agents that are very good at doing scheduling of tasks. And at the multi-cluster level, you may need agents that are good at scheduling actually across centers. And that's really when we think about the HPC center of the future, that's the level that we want to operate at. But these other levels are important too. And just to work on this task, we realized early on that we needed this skeleton template of a server that we could deploy on these multiple levels. So we designed the MCP server. It's a great name. I know. It uses MCP, the Model Context Protocol, which is the standard that the agents are going to use to discover functions. So for example, SPAC find. Now, when I first heard of MCP, I was like, oh, that sounds really complicated and interesting. And then you kind of stare at it and you scratch your head and you're like, it is an API standard. And that's it. And that is absolutely true. Now, a very simple way to think about our software, and this is the way that we designed it, we wanted it to be simple, is that when you make a tool for an agent, it is, for the most part, a Python function. So when you run your MCP server, when you start your MCP server, you give it a YAML configuration file that basically has a list of paths to Python modules, functions to import. So in this example here, this is for a server that we want to run that's going to do stuff with SPAC. So at the top, we see a lot of HPC functions to interact with the file system, to build or do stuff with SPAC, to interact with Git, with a database, and then we also see functions to interact with Flux. This is via our library, Flux MCP. If you are interested in these libraries, they are on GitHub, Flux MCP and HPC MCP under their Converged Computing organization. And please ping me after if you want more information or just to remember these links. So the next thing that we realized over time is that this serial interaction with agents, when you're doing something like building a container or SPAC installing, which takes a long time, you don't want the agent to be waiting. And actually, in most cases, the server, waiting time is going to time out. So what we added to the MCP server is real-time events. What this means in practice is that the agent is able to see that it can subscribe to an event stream. When it subscribes, as it's looping and doing other things, we will receive events and we give them to the agent so the agent can respond in real time. It should go without saying that we use asynchronous concurrent requests. Between MCP servers, we would use async io.gather, so it gets sent out to all of the children at once. And here's the cool part. Because we work on Flux and we think of everything in graphs or trees, this agentic server actually integrates into a hierarchy. And let me show you what that means. So this is actually a hierarchical agentic server to support science. What this means is that although you can deploy one MCP server on your local machine to run a small set of functions, any single server can act as a hub, as a worker, or both if you're in this middle layer. And what this means in practice is that you can send some kind of request to a parent. So let's say that you send a job to the center hub and you say, hey, center, I'm looking for resources to run this specific work. The center can see its two children, cluster A and cluster B, and then ask the two children, hey, each child, do you have the right resources that this user is wanting? And then as you move down the hierarchy, you can basically ask more nuanced or more detailed questions about what is available. And then the same goes true when you're moving back up. Now, important to this interaction, as I mentioned, it sounds kind of agentic. We have a resource secretary that runs on each of these particular MCP servers. So we call this the resource secretary. That's the project. It's also on GitHub. And so the resource secretary is basically going to come up on some kind of computational resource. And I say this because it could be a single machine, it could be an edge device, it could be an entire center, or it could be something above that, right? But it is going to come up, and what the resource secretary does is it has a provider interface. And you can see these on the right side here. And so when it comes up, it's going to dynamically discover all of the different providers that the resource actually provisions. So the workload manager, what software providers, storage. So then when a parent or actually an agent from the bottom asks it a question like, can you do this particular thing? It will be able to say, okay, looks like I have a Kubernetes cluster and the Kubernetes cluster has this kind of storage and this kind of network. Yes, I think I can, or no, I think I can't. And a provider interface can literally be almost anything. This is the example that we started with in our early work. So these are the kinds of tasks that the resource secretary agent currently handles. The first we call negotiation. So this is basically, hey, agent, can you satisfy this particular request for work? The next is selection. That is what it sounds like. Here's a set of choices. Please choose the best one based on the resource providers that you see. Dispatch. Here is a request that is coming in as a textual prompt. I need you to transform this into the right format for the workload manager that you have. Submit the job, monitor it, make sure that it's running, and then return something back to me. All right, so how have we been testing this work? Well, we started with simulations. We did simulations to test negotiation, selection, and dispatch for our agents. Here's a summary of what our experiments looked like. The basic idea is that we wanted to compare what the agent did to a ground truth. So for negotiation, what we did is we came up with 200 simulated workers, and we actually have a pretty cool algorithm to do this, where we have an archetype for a type of worker. So a cloud archetype, an HPC archetype, and then a standalone archetype, which could be a single VM or it could be an edge device. And so for each archetype, for example, an HPC archetype is going to know that it will select a workload manager that might be Flux or Slurm or Cobalt, and it's going to have some cardinality of software providers, and it's all randomly generated with distributions. And we have a paper that I can show you if you're interested in how we did this. We also had programmatically generated prompts on 10 different dimensions that would range in incrementality and in complexity. Then we also had an audit strategy so that we could run the negotiation and then very carefully look at the entire result that we got back. We could compare what the worker reported was its truth to the actual state, because remember, we're running a worker, a server, that knows the exact truth of what it has. So we just compare that to what the agent reports to see how often it hallucinates or maybe gets it wrong. And then we can also assess expected versus actual tool calls, Because, for example, if you are asking an agent to do something very specific, there's going to be a certain number of expected tool calls. And then there's going to be like other stuff that it does that you didn't really want it to do. So that was our negotiation. For selection, we came up with 8 different selection algorithms, 6 traditional, and then 2 agentic. And then we again had an audit strategy. And this strategy was based on comparing the expected queue pressure, or basically jobs building up in the queue, and then agreement between algorithms. And then finally, for dispatch, this one was very cool because we again had actually a better designed even matrix of prompts that would range from like the full command to just total natural language description of a task. And then, of course, we looked at different metrics, comparing the agent's ability to transform, submit, monitor, and report back, because that's his job. That's what he needs to do. Okay, so let's talk about the results. First, for our negotiation simulations. The agents were highly accurate, 87.71%. What you're looking at here is a confusion matrix, the worker truth versus the agent verdict And so this is basically the idea that like we know the true state of a particular worker, and then we also have how the agent is reporting if it's able to do a particular amount of work. And what we see is that the agents are very good at detecting compatible and incompatible resources. The most incorrect responses we saw that were basically based on what we're going to call improper lookup. So for example, if it was looking for a certain piece of software, maybe it didn't check all of the package managers it had available, because every package manager is going to have a set of tools where you can ask like, hey SPAC, do you have LAMPs installed? We also found in practice, and this was a really interesting observation, that giving more output or giving the same output that you give a human is not always the best thing. So for example, for those that have used SPAC, if you do a SPAC spec or SPAC info, you get a huge amount of information, not just about a package information, but all of its dependencies. And what we found in practice is that when you do that, the agent can sometimes confuse the version of a dependency with the version of the software. So what we learned from this is that we can't use the exact functions provided by SPAC to do this work. If the agent needs to know the version of a piece of software installed, we need to give it back just that version and not a lot more information that may be actually confusing. Okay, so now we're looking at accuracy versus specificity. What do I mean by specificity? We came up with a specificity index, or SI, where an SI of 1 would be like a really simple, very unspecific request. Run lamps. A specificity of 7 would be very specific about many different dimensions. So like use a container, for example. And in practice, what we found is that the lowest specificity score, the SI of 1, there wasn't enough information there. So we can see that for the standalone and the cloud, the accuracy, the correctness of the agent, it kind of went down a little bit. Now, as we increase the specificity score, we give it more information, but when we aren't so specific, it starts to increase. Now, where we see it really fall off, especially for the HPC archetype in purple, is once we got up to scores of 6 or 7. And I'll give you an example of why this happens. So for 7, we often would say use a container. And what we saw in practice as we watched these runs, as we looked at the results, is that the agent didn't often have enough detail to know how to find or to use it. So for example, sometimes it would say, okay, I need to use a container, and it would maybe confuse Podman with Singularity, or would look for Docker, but it didn't have Docker, or it wasn't clear to it that it needed to run the application using the container. It thought it needed to do something else. So this, I would say, is an issue with how we prompted, that we did not give the agent enough information for how to do the task. Okay, so here, what we're looking at is the accuracy of our secretary agent for this negotiation versus the tool call scores. So what we did for each execution is we came up with a tool call score. This is based on the actual versus the minimum required call. So you can imagine that there's a minimum set of calls that are required to kind of discover the needed parts of the environment to determine if something could run. So you need to maybe look at software, the workload manager, the busyness of the queue. So you can imagine making too few calls or too many calls. We require in the prompt the agent to make at least one call. And we do this because when we didn't do it, it would often sometimes just hallucinate the entire response. We found that when we required to make at least one call, it didn't do that. So what you see in the result here again is that the HPC environment is more challenging. This could be due to just having bigger cardinality of, for example, software package managers available. This kind of reflects the real world too, doesn't it? And what we also found is that a high value can precede failure. So why might that be? It's usually because the agent is looking for something that it can't find. So it's making a lot of tool calls and searching, and it doesn't find it, and then it fails. Okay, let's talk about our selection simulation. So here what we're looking at is what I talked about earlier. Worker pressure, which is basically like as the simulation proceeds, we should basically see that each selection algorithm is adding jobs to the respective queues. So this happens over time, and so we see the expected pattern that we wanted to see. We also noticed that agentic selection was notably different. So looking at the right, what we see is agreement of selected workers between algorithms. And so those yellow boxes there, what they're highlighting are basically that the agentic strategies, they kind of look different, don't they? So that is an agentic strategy based on cost and then just a general agentic strategy. They tend to have less agreement with the more traditional algorithms, such as just having a sort and then getting the first ready cluster, or the minimum cost, or the queue depth. So this was very rudimentary preliminary work. We need a lot more work here. But the point and the reason we wanted to share it with you is that there's a lot of interesting development and work to do with respect to agents making decisions based on resource selection. Now here is, now we're going to be looking at our dispatch simulation. So just so you understand what's going on here, this is where you're sending a piece of work to a specific agent and you're asking it to transform it into the right workload manager object, whether that's a Kubernetes manifest or a Flux batch or a Slurm batch script. Then you're going to have it submit the job, ensure that the submission was successful, monitor it to make sure that it's running, check the status, briefly check the log to make sure there wasn't an immediate failure, and then send back the result. And so what you're looking at here is what we're calling tool call redundancy. We would expect in like the perfect execution for the agent to do each of these things one time. In practice, we get pretty close to that, but there's a big variance in job submissions, and likely that's because the agent got it wrong, transformed something and tried again. And then the status checks, it does a little better. We see the variance goes down. Log retrieval is about the same. And then we have a few, we have just barely, we have a very small set of cancellations, meaning that the agent did submit and then went back and changed its mind and decided to cancel the job. So this was also a very good result for this preliminary work. Now here is how we are assessing the goodness of the submission, because you can imagine that the agent submits a job for sleep, which is totally wrong because we wanted it to run lamps. What we were actually running is lamps across 5 different nodes. So just to tell you, we did these runs manually, just running in a loop, and we found that the expected running time was about 2 minutes and 30 seconds. So the range of 148 to 155 seconds is fairly reasonable. This again was another great result because the agents did very well. That small bar of 0, that's where the agents were not successful to basically submit the work. They returned back a runtime of 0, which means the job did not happen. Okay, so another question that we're looking at is, how does prompt style influence dispatch success? So you'll remember that I mentioned that we generated this matrix of prompts in different types. What that means in practice is that every feature of the prompt, so the manager, the resource, the configuration, For lamps, one of the features was whether you ask it to add the no site flag or not, and then whether we ask for affinity. And then we had different values to define that. So giving it exactly, giving a descriptive, giving sort of a verbatim. And then what we're able to do is generate an odds ratio. So we can look at the odds ratio for each of these prompting strategies for each different features to determine the relative contribution of the feature to the dispatch being successful. So as an example, for odds ratios, an odds ratio of 1 saying, okay, this particular combination has no different effect than average. Not really that interesting. A score of 5 would mean that using this particular prompt style in this particular feature makes the agent 5 times more likely to have a successful outcome. So then likely, or sort of reasonably, when you drop below 1, so for example, if you get an odds ratio of 0.2, that would say actually using this value makes the agent 5 times less likely to succeed. So this is, again, early work, but what we're learning here is that different prompting strategies for different features, they do matter. All right, so now let's talk about translation experiments. These are experiments where we want agents to be able to take some description and then execute work from it, which you may agree, you may not agree, is the direction that agentic science is going in. So here's a summary of some of our early experiments. We actually did about 5 or 6, but I'm just going to be sharing 3 with you today. The first was a scaling optimization study. So we took our early 2025 study that I already shared, and we said, we're going to do this better. We're actually going to do it again, but we're going to have a more kind of hardened software to handle it. So this was version 2 of the scaling optimization study. The next experiment was based on, again, job specification translation, but we kind of scaled it out. So we basically had 1,000 open source job specifications from GitHub. We actually have a database of over 33,000, but we had a certain number of tokens, so we just used 1,000 for our experiments. This is a cross workload manager. So anything that is on GitHub, we found it. We instruct the agent to take the job that we found on GitHub and convert it to Flux. And we did conversions to Flux only because we have an easy way to validate with Flux. You can validate with the Flux validator or with just submitting with a dry run flag, which will go through the same internal logic that the validator uses. And then we're able to basically do validation in this way that's kind of very hardened, where we're validating with Flux itself. But we can also parse the commands. We can look at it. There's other different ways to validate it. And this was actually very cool because what we did, we kind of combined these two. We took the containers from our scaling optimization study. We manually created commands. So for example, lamps run this work. Lamps run this work with affinity. And then we had the agent take those commands and translate them from Flux to Slurm. And then we could use the Flux operator and our Slurm operator, meaning we have Flux running in Kubernetes and Slurm running in Kubernetes, and we could actually compare them side to side, apples to apples. Because before we initially would, use a Slurm VM-based approach in the cloud, but we thought that this was more fair to be running in pods in Kubernetes. So that was the job specification translation and translation performance study. The final study I actually already previously mentioned, this is workflow orchestration, where the agent is given access to a scoped file system root for a working directory. And then what we did, so if you're familiar with SnakeMake has these things called wrappers. They're like components or steps in a full biosciences workflow. And so we give the agent access to the entire suite of wrappers, and we say, hey, agent, I need you to design this snake file, figure out each step, put it together, execute the entire thing for something like variant calling. So here we have results for our scaling optimization study for AMG and lamps as before. Now, the first thing that probably sticks out to you is, wow, there's a lot of variants for AMG, not so much for lamps. But let me tell you why that is. in this optimization study, we're not just giving the agent a problem size and asking it to execute across 5 nodes and adjust parameters as needed. We're asking it to figure out the biggest problem size that it can support at one node. So what this meant for AMG is that it came out with different problem sizes. So we're kind of seeing plots, especially for AMG, where we're not comparing apples to apples. We're seeing AMG run the same problem too, but with different matrix problem sizes, different dimensions. And so that's why the variance is much higher on the left. Now, the interesting thing with lamps is that the agent was very good at choosing the same problem size across the different studies, because what this plot is showing is actually multiple entire optimization scaling studies for each application. So what that tells us is that for different applications, we need to think hard about the prompts that we give for how it optimizes at some size. So for example, with AMG, if you don't tell it anything, it will often choose a really big problem size, get killed early on, and then kind of flounder a little bit. It's much better to tell it to start at a specific problem size and then go up incrementally until it figures out what it deems optimal. Here's another example for the OSU benchmarks. So this, we were asking the agent to basically take a command for one workload manager. So in this case, it was Flux, and translate it to Slurm. So what we want to see is that the Flux to Slurm translations, the actual performance of them, is comparable to Slurm. And that's what we see. So in the plot on the left, there is an orange line there. The orange line is actually under the green line. So Slurm is underneath the Flux to Slurm, which tells you that they were basically indistinguishable. Now, the most interesting thing in this plot is actually just that Flux as a workload manager did not perform the best in terms of OSU latency. And this was very interesting to me because I had never run Slurm in this context, and I had never seen latencies that were around 7.41. That was really cool. Now for OSU benchmarks, and I apologize, the colors are a little bit different. What we want to compare on the right side is that Flux to Slurm, which is in blue, and then that to green. So you'll notice that the blue is slightly higher and then has more variability than its counterpart. And this is because in practice, the agent wasn't perfect in the translation and maybe was inconsistent with, for example, defining affinity flags. But overall, they're still relatively close together. And then interestingly, Flux, which is orange on the right, is actually kind of is lower again for latency. So I guess there's a trade-off between the two, and I do not want to make a comparison between Flux and Slurm. They're both very good. The interesting thing and the important thing to note here is that the agent did well to do the translation, and we can prove that the translation was of good quality because it is comparable to a manually generated job spec. Okay, so now what we are looking at are job translation issues. So for the times when we took those 1,000 job specs and we did the translation, we wanted to understand what were the issues with performing it. And so we created 3 categories. The first was no analogous. And so that's when the agent would report, I can't transform this flag because there's literally no analogous thing. Missing meant that, okay, this entire thing is actually missing, and then a mixture between the two. So out of the 1,000 job specs, we could only do 982, which meant that there were a subset of them that the agent determined were not actually job specs. And we verified that they tended to be like batch scripts that would be given to a workload manager. I'm not sure how that would work. We validated these with a Flux dry run to make sure that they were actually generated valid Flux job specs. And importantly, I need to point out here that Flux does not have a memory flag. And so when you look at this result, the biggest issue that agents reported was with respect to output and error templating. So if you've looked at Slurm batch scripts, you'll see kind of the percent symbol and like a J. There's lots of shorthand symbols that you can make to define how you want your output files to look across, for example, a set of them. And so Flux does not have that as analogous thing, so the agent is going to report it. Memory allocation is the next one. That's why we're saying, you know, Flux does not have any kind of memory flags, so the agent would report that too. And then the issues get smaller, so there's issues with process topology and binding. Sometimes the agent got it wrong or it just totally missed that a broker flag in Flux maps to a different flag in Slurm. GPU specification, sometimes the agent would have a hard time with, you know, Slurm res to something in Flux just with simple GPUs. And then, of course, we had issues with MPI and launcher, job arrays, environment management, and then, of course, dependencies and scheduling. So these are kind of the summary of our issues. Okay, now let's quickly look at some workflow orchestration with SnakeMake. This work is very much still underway, in progress. We're testing different kind of traditional SnakeMake workflows like the variant calling tutorial one, quality control, trimming against gold standards, which are human-written snake files. So here's an example of result we might get of a final snake file where the agent executed different steps. And it would say, I successfully executed this workflow to perform these tasks, and here's the result file. This is coming out, again, very well, and we hope to have results to share with you shortly. Now, what work do we have in progress? What is next steps? We are catapulting down this list. We believe these are important things that we're going to be working on. We want to basically model different costs into our resource providers for the MCP server, so that we'll basically be doing an updated set of selection experiments that better take into account cost, and specifically that like one type of GPU is a lot more expensive than another type. We are working on a Kubernetes operator for agentic workflows, because although the MCP server itself can run in Kubernetes, we don't explicitly have an operator yet. And we have a lot of work going on with respect to an HPC center of the future. So what does that mean? It means that we're thinking about multi-cluster scheduling algorithms and infrastructure. All of those steps that we've talked about today, from job negotiation to dispatch and then updating some kind of state. And you may or may not be aware the lab has the future generation HPC center. That's FGHPCC. And you've probably heard of the government initiative Genesis. We are actively involved in that too. Looking forward, the HPC Center of the future is built upon convergence, modularity, and agency. It is empowered by the workload manager. It is a proactive, autonomous platform that will accelerate scientific discovery. So thank you so much for having us today. We will now take some questions.
Okay, thank you, Vanessa, for the nice presentation. It's amazing, all the work you do. Anybody has a question for her?
While the audience is warming up, I want to mention something. So we have a chat, all the team attending this conference, and we were just commenting how spectacular is what you have been doing over the last year. So, yep, thank you so much for presenting this.
Yeah, it's our pleasure. We are very grateful to be invited, and I hope to be able to be there in person soon. I am traveling again, so maybe next year.
Oh, awesome. Okay, so one of the questions that we were discussing internally is how many people have been involved in the agentic, the three agentic process that you have already shown today?
So to be totally frank, it's primarily me that does the work and experiments, but I work closely with Dan because I need someone to talk to and to share results, and I do present. We have a weekly meeting as well, but it's primarily me that does it.
And how long it took for you to commit with this? So we are talking about 1 year?
So our first, I told a little bit of the story in the talk, but we were working as like a larger team on just a really simple task of like, convert this JSON to like a slightly different format of JSON. And I went off on my own and I was like, maybe we can ask a little bit more of these agents, because I was using them personally to do like, make me a recipe for lemon bars, and it worked really well. So that was at the end of 2025, and that's when we did the first agentic scaling study in Google Cloud. And it worked so well that I just started writing experiments for all the kind of stuff, because I started to think like, what does the HPC center of the future look like? What are all of these tasks that could be agentic that currently aren't agentic? And so I started putting that together, those experiments. I would say I really started them after March of this year. So it hasn't been a huge amount of time. And actually, we've gone into really other cool work that I am looking forward to talking about at some point related to quantum scheduling. So, so to answer your question, a fairly short amount of time.
Thank you so much.
Yeah, thank you for having me. Have a great time on your trip. I know you're going somewhere fun. I forget where that is, but yeah.
Bye, thank you.
Thank you.
Okay, so this is the last talk that we have for today. Well, I'm going to get ready for the wrap up. So how are you feeling? Tired? You must be, because it have been quite intense days. Hey, I hope that over the last 48 hours, you got quite a nice number of ideas and things to think about, things to test, to eventually to implement in your centers. I want you to thank all the people that have been involved in the organization of this event. So people in the back, thank you so much. People from Focus, so thank you so much for making this event very special. Also to the sponsors, who, well, we could potentially do this without the sponsors, but so thanks to them, you don't have to pay a thing. And, and thanks to them, we are having the quality and the environment that we have now today. So it's instrumental for this to happen this way. So thank you so much, all the sponsors that have been contributing into this event year after year, actually. And yeah, so as we conclude this session, I want to thank all the audience to come to all this way here, and most of them coming year after year as well. Thank you so much. We really appreciate that. I hope you enjoy it, and I hope we will see you next year. Thank you so much.